Good morning, my name's Jason Cox, Energy Upgrade Leader at Armstrong Fluid Technology, and I'll be taking you through this morning's presentation. So today we're going to be addressing the following points and how they impact a wide variety of buildings across the healthcare estates. We're going to cover off, but it won't be limited to mechanical system efficiency opportunities, where we can get started, the Armstrong roadmap to energy reduction, data and efficiency drift, pumping basics, applications for retrofits, and then finally we're going to have a look at some real world examples. We're also going to be taking your questions at the end of this presentation. So before we get started, here's a small intro into us and our mission. So Armstrong Fluid Technology is a global company with our head office in Toronto, Canada. We've been in business for just over 84 years now and specialise in products and solutions that drive efficiency and sustainability through mechanical plants and buildings. We're now manufacturing on 4 continents and we distribute worldwide. As a company, Armstrong are committed to addressing the climate changes of our planet through the delivery of our technology in customers' projects, and we have committed to a reduction of 2 million metric tonnes of CO2 by 2022. With the NHS working alongside government climate change plans to achieve net zero emissions by 2050, and some trusts even aiming for 2030, you can see that Armstrong are well placed to support these challenges. Additionally, we have committed to the World Green Building Council's Net Zero Challenge to reduce emissions of all internal operations to net zero by 2030 ourselves. And most importantly of all, we have also made a commitment to make these energy upgrades cash flow positive for our customers from day one, making them an essential part of any guaranteed savings scheme, whether that be through the Energy and Carbon Fund or similar schemes. So where is the opportunity for Armstrong to support these objectives? Studies have shown that heating and cooling costs currently comprise of around 56% of a building's energy use, and this percentage is increased as the energy efficiency measures in other areas continue to penetrate. One example is the implementation of LED lighting, which can reduce the lighting percentage from 15 to 5% or less, thereby increasing all the other components proportionally. While the blue area you see here, or blue areas, are understood and advances in efficiency continue to make significant progress, little is happening to address the heating and cooling contribution of the energy problem. This is where we have approaches and solutions that can drive significant reduction within hospitals and across the healthcare estate. But why is it so hard to achieve significant energy reductions in existing buildings' heating and cooling systems? Why is that part of the system such a challenge? Well, firstly, a typical HVAC system design is fundamentally built on these islands we see here of functionality, with attempts to provide integration through independent control of the islands and through cross control. However, over time, in a HVAC system, there tends to be drift into islands of functionality. There are many reasons for this. Some common ones include, but are not limited to, manual interventions to address tenant comfort needs and issues. You can have changes in functionality of the building, load variations, and so on. These issues end up trapping approximately 30 to 40% of energy in energy wastage. So what we can see here is a traditional roadmap. So what we're looking at is how to address these issues. So if we're going to really drill down and focus on the HVAC system within a hospital, for example, most companies will approach that through what we term a traditional HVAC upgrade. And as a timeline, this is what that would look like. So first of all, you would spend probably 3 to 6 months in the data acquisition phase, harvesting the data from the system to understand the size of the plant and how the plant's performing. And by plant, we're talking about the overall system here. Following that 6 months, we would then enter a period of data analysis to try and understand that data. And once we're informed by that data, we'll then start to put a cost plan together, which again can take another 2 to 3 months. And then we enter the all-important budget approval phase, which again can take quite a while. But the real point here is that the project doesn't end up getting implemented until 16, 18 plus months. So you don't actually see any savings up until that period. A very long time passes. What we're saying here at Armstrong Fluid Technology is to follow our roadmap and our pump first approach. So you can see 3 clear phases on the screen. We've got the pump, or pump first, and by replacing a pump you can look to save up to 10% of the energy within that system, and you can start to see savings from day one. And that's the difference between what we're talking about here and a traditional approach of upgrading the entire system from the get-go or the major plant. So once we've surveyed the pumps and we've replaced the pumps and we start to see a financial saving and we start to see a carbon saving, we're remote monitoring that pump, so we can also harvest the data from the system through the pump, so we're learning whilst we're saving, and then that can inform us of optimization opportunities. Now that may be Armstrong controls being added to the system. It could be converting the system from a 3-pipe to a 2-pipe system, and all manner of other types of optimization. And within that phase, that second phase, you can look to save an additional 30% of energy. And then finally, we get to the larger plant, your chillers and your boilers. But at this point, because we've been using our pump manager and our remote monitoring, we know what we don't just know the building load, we also understand the load profile. So what usually happens at this point is we end up reducing the size of the replacement chiller over and above what's already installed, which is a big benefit from a CapEx point of view. But we can also then select the right chiller or boiler at its best efficiency, so it can spend longer at its highest efficiency, and therefore you get longer savings or better savings. So let's just compare those two. So there we have the line that we saw before, which is the traditional approach, data acquisition, understanding the data budget plans, and we're not seeing a return on investment or any savings whatsoever for the first 18 months. The blue line you now see is following our Armstrong's pump first approach. And as the line drops down, we can see the pumps have gone in and we start to make a saving from day one. We can then see around the 6 month to 9 month period, the optimization kicking in and making further savings. And then finally, the larger plant being replaced. And 2 things have happened here. One, we've been saving from day one. And 2, we've ended up with greater savings overall. And those savings are going to roll year on year. So it's an approach that really does make sense. And there we see the wasted opportunity that we've unlocked by following the pump first approach. So we're going to look now at flowing forms, and we're going to look at pumps themselves and how we tend to integrate them. So through our real world experience and real world implementation, we've learned that pumps are at the buildings such as hospitals' heart, and they're acting like a heart in a body, sensing the building's energy and the comfort demands through increased requirements for heating and cooling. The key to benefiting from this is true integration between the systems. But why is it so hard to achieve significant energy reductions in existing buildings with heating and cooling systems? Well, as we touched on before, a typical HVAC system design is fundamentally built on islands of functionality, with attempts to provide integration through independent control systems or islands or through cross control. But over time in a HVAC system, we tend to get drift in the islands of functionality, and there's many reasons for this. This can equate to up to 30 to 40% of energy wastage in that system. And we tend to refer to this as we move through this presentation as energy white space. So the energy loss between the islands, if you like. By starting with an upgrade to intelligent pump, so by following that pump first approach, on the distribution side of the system, we get a much better understanding of the building load, the characteristics of the system and its components. And this immediately brings us a number of things. As we previously saw, it brings us up to 10% energy savings. It also makes the system operation transparent to the BMS system, and there's many benefits to that, of course. And like a healthy heart, it adds to the efficiency of other equipment in the system by ensuring optimal flow to towers, chillers, etc. And most importantly, it can be cash flow positive, or a cash flow positive investment from day one. Now we add intelligent pumps. Now we've added our intelligent pumps to the condenser loop, we get a better insight into the tower profile. These insights help us make informed decisions on the next cash flow positive steps to an upgrade, which could include, but are not limited to, control and optimization of the condenser loop. We could look at converting the towers to variable flow, or we could even header the towers. These integration and optimization steps further provide flow insights into the plant and building requirements that can deliver up to 30% energy savings. Only after these steps are complete do we finally move on to the larger plants such as boilers and chillers. And in this instance, we're looking at a chiller. So now with the building demands clearly understood through transparent flow and load information, the chillers are ready to be sized and staged correctly. This right sizing delivers up to an additional 10% alone in savings. In practice, we see the plant systems are often oversized from day one, and this will come as no surprise to anyone on this webinar. In an upgrade, the tendency is to replace like for like capacity, 500 kilowatt chiller for 500 kilowatt chiller, and so on. While the building demands have changed over time since that original chiller or boiler, for that matter, was installed. Add to these the tendency to apply safety factors, and this further adds to the oversizing. So it's critical that we understand what the requirements of the building are, rather than just what is installed already and what we are replacing. With the pump first approach, your path to the plant upgrade is provided with transparent information to right size the plant and achieve optimal efficiency. And as we said before, we're doing all of this whilst we're already saving money. So how is it possible to provide this degree of transparency? Where is this data coming from, and how is it collated? Well, it is the evolution and transition of connected devices that provides a degree of transparency to data previously unavailable. This is what is driving the industry. So what is driving the industry's rapid expansion in this area is connected devices, which firstly are a lot more cost effective these days. Data is easier and less expensive to transfer. Cloud storage is a fraction of what it used to be in terms of cost. And many companies are providing storage free to consumers to entice them to their services. And then you've got the hardware. So things like sensors, devices themselves are very inexpensive. Wi-Fi chips, GPS tracking, vibration, sound, so on. All small and all fairly inexpensive. Our design envelope integrated sensorless and connected pumps and controls bring all of this capability to light, and we do it now, we do it today. We have working systems that are already operating in this fashion. So you've got your pumps installed, you're saving from day one, you're following the roadmap. So let's have a look at this pump manager and the software and the remote monitoring and what it gives us. What would it give you in your hospital or across your healthcare estate? Here's a great example of the power of data and analytics. This is actual vibration data pulled from a site in May 2019. So what we've got here on the screen is 3 identical pumps, same size, model, all installed in the same building on the same day. You don't need to have an advanced degree in statistics or mathematics to realise or recognise that one of these pumps is experiencing a different level of stress. In this particular instance, the pump at the bottom right of your screen here is experiencing a deadhead condition. It was running, but there was no flow. So this could have been caused by many reasons, probably a closed isolation valve or something daft like that. Pump Manager gives us early warning alerts using real-time data, which means predictive maintenance can be employed, thus avoiding critical failure of plant. So in something like a hospital, this enables us to maintain patient comfort at all times. And of course, that is critical in this type of building. Beyond fault detection, we also have building equipment trending built in. such as profiling. So we can profile flow, head, power, amongst other things. This is important because flow from an individual piece of equipment is rarely collected on site. Flow might be collected across the system, and this provides insight into the contribution of individual pieces of equipment. More importantly, collectively, it provides the basis for flow informs, and flow informs is core to our energy upgrade roadmap that we mentioned earlier. The power of this transparent data and analytics is in avoiding the energy drift in projects, which often results in savings degrading. Studies have shown that this can amount to as much as 30% in as little as 3 years' time. However, through the use of this transparent data in our active performance management, your savings can be sustained through the longer term, ensuring realisation of your initial value proposition and return on investment of your products. So as I mentioned before, flow informs, and flow informs can help you get started on your energy roadmap, but more importantly, it helps you maintain your savings through the longer term. So let's have a look at the life cycle costs of a pumping system. So here on this pie chart, we can see the makeup of energy throughout the life of a pump. So 40% of it is made up through the energy burnt by the pump. And then there's 10% for the pump itself, 7% for the installation, and so on and so forth. But it's that 40% that we want to focus on here, and how we can affect the efficiency and the savings on that 40%. And on the left-hand side of the screen, you can see some of the reasons and some of the things that can affect it. Optimized capacity of motor power, pump motor starting, quadratic pressure control, so on and so forth. And we'll start, I think, with sensorless control. Have a look at that. So flow data also supplements analytics of potential systems issues outside of the pump. Take the BMS, for example. So the BMS may send a signal to an isolation valve to open, but may not get a return signal back from the valve to tell it that it's stuck 2/3 open. However, the pump will know this based on the resistance that it's feeling. Alternatively, if condenser pumps are working harder than they were, say, 3 months ago, to deliver the same flow they were delivering 3 months ago, there may be an issue with the pump, but it's more likely that there's a partial obstruction in the system. Say the towers need cleaning, something like that. And all of that could be picked up through the pump. So we said we'd look at sensorless. So sensorless control monitors and controls the pump without the need for a physical sensor. So you don't need our pump and a sensor, the pump will do it all. And this simplifies commissioning. It makes it easier to achieve a designed energy performance, which is critical to getting that return on investment you were promised at the start of the project. And it also provides flow measurement without the requirement for a flow meter. So you can see we're reducing down the number of components or additional components needed over and above the pump. All sensorless control pumps are tested complete with pump, motor and controls package by recording the flow, head, power and speed at 10 different points along the maximum speed curve seen here, and also all of the speeds, all the way down to the minimum speed. All this data, or pump coefficients as they're also known, are then uploaded into the controls map so that we know the exact flow and head at any power and speed, which can be read by the controls on the testbed and also on site, and can be remotely viewed through your pump manager software. This is cutting edge technology for pump controls, although here at Armstrong we've been using this type of data in selection software for over 25 years now. The success of our solutions can be seen here and in many cases. Studies where Armstrong products have proved themselves time and time again over the years. So some of the examples here in Canada, the US, China, India, and of course here in the UK, where we've continued to deliver our energy upgrade projects in healthcare facilities over the years. We're currently engaged with several large healthcare projects across the UK. Some of them are part of the Carbon and Energy Fund framework, others are part of the retrofit framework, and then we've got multiple projects ongoing and complete where they're being delivered via the energy upgrade team here at Armstrong directly with the hospitals and healthcare facilities themselves. So hopefully we've addressed most of the agenda points that you can see below. So I'll now hand you back to our host and look forward to the questions and answers session shortly. Thank you.